Hey, Jonathan here at Colfax Math. Today I was going to go over Chapter 12 in our IB Math SL book. Chapter 12 is trig, periodic relationships, areas, sectors, ratios, and all I'm going to look at right now is 12.1 and 12.2. So 12.1 is radian measure, arcs, sectors, and segments. And how this works is we have a unit circle, and by definition it is called a unit circle because the radius is 1 unit. So the circumference of a unit circle is 2 pi r, and r is 1. So the way all the way around the outside of that circle could be measured as 2 pi. So all the way around is 2 pi. It's radian measure. And there's a lot of advantages of using radians. The biggest advantage is that it is unitless, so you could attach any unit you want to it. So 45 would be right here. So number 1 is 45 degrees. If I want to convert that into a radian without a calculator, so that means exact value, all the way around is 2 pi, halfway around is pi, a quarter of the way is pi over 2, and this would be pi over 4. So 45 degrees and pi over 4 are the same thing. Jumping down to number 2 here, pi over 6. Pi over 6 is 1/6 of the way to pi. Pi is 180 degrees, so 1/6 of 180 would be 30 degrees. Express each angle in radians. This is with the calculator, so I have 10 degrees. I want to multiply it by a factor of 1 so as not to affect the value to get into radians. So I'm starting in degrees. I want radians. I know that 2 pi radians is equal to 360 degrees. These things have the same weight, so I'm multiplying by 1 and not affecting the value. So I'm going to take 10, you see that, 10 times 2 pi divided by 360, and I get 0.17 radians. So that's an approximate value because I use the calculator, and it's a radian measure. And lastly, number 4, again, these are exact value because it says no calculator. These are approximate value. So number 4, I start with 1 radian and I want degrees. So to get degrees, I multiply by 360 degrees over 2 pi. As long as this thing has a factor of 1, like it could be anything. So I'm actually going to do 180 degrees over pi. Because this and this have the same weight, it's the same thing. I'm multiplying by 1. So I have 1 radian times 180 degrees divided by the pi radians, and I get 57 degrees. So that's approximate because I use my calculator from radian to degrees. Approximate from degrees to radian. Exact are going to work out to be 30, 60, 90, or 45 exact value triangles. I'll just say one last thing here about radians. I know that circumference is equal to 2 pi r. 2r is the same as diameter, so I could say that circumference is equal to diameter times pi. If I measured that circumference in inches, I would have measured that diameter in inches. So if I divide both sides by diameter in inches, I have pi by itself. And then now I can see that pi is a ratio of circumference to diameter, but my units of inches cancel. And that is why radians are unitless. And that's really kind of the power of working with radians. So there's the only difference between this and this is exact and this is approximate. And it's also the same exact thing as 180 degrees, but now I have units attached to it, so this is a degree unit. I don't write units on these because there are no units. Sometimes I could put rad there, but it's really just a placeholder. Okay, so that's section 12.1. And then we'll turn our books to section 12.2. And this is really lengths, sectors, segments, arcs. And before I do any of these, let me just go over some of these definitions. Here's a circle with its center point, its radius, and then this right here is a slice of pizza. That's called a sector. The area of that sector right there is the area of the whole circle multiplied by the ratio of what you want over the total. So let's say this is 45 degrees and a radius of 7 feet. Area of the whole circle would be pi r squared, 49 pi, and that's going to be square feet, times the ratio of what I want over the total. So it's times the ratio of 45 over the total of 360 degrees. So it's 49 pi times 45 divided by 360, and the area of that sector is 19.24. The area of this, the length of an arc, so if I wanted the length of the arc there, I would do it pretty similar, but I wouldn't use area, I would use circumference. I'd use circumference of the circle, 2 pi r, so 14 pi is the whole circumference around. I don't want all of it. I only want 45 over 360 parts of it. So then I do that on my calculator. 14 pi equals times 45 divided by 360, and that would be 5.5 feet. So all the way around the circle is 14 pi, whatever that is, 43 feet, and the length of this arc is only 5.5 feet. And the sector, the shaded in region here, the pizza there, that would be in square feet. Okay, so with all that said, let's take a look at some of these problems here. Let me just take a look at number 4. So on number 4 here, I have a circle, I have a sector. A lot of these are on the SAT. This angle in the center here is theta, and then in the description it says theta is equal to 1.5 rads, and I have a radius of 10. So the first thing I'm going to do is find the area of that sector. So the area of the whole circle is pi r squared. Area of the whole circle is equal to 10 squared pi, or 100 pi. So the area of the whole circle is 100 pi. I don't want the area of the whole circle. I only want the area of 1.5 radians over the total. Well, the total is 2.5 radians. So as radians over radians, my units cancel. I'm multiplying it by the ratio of what I want over the total. It's approximate value problem, so I take 100 pi times 1.5 divided by 2 pi, and the area of that sector is 75. What is that, 10? I don't think there are units attached to it, so that's just square units. So that's the area of the sector. I don't want the area of the sector. I actually only want this shaded region here. So I could see that shaded region is going to be the sector minus a triangle. So that triangle looks like that. where this is 10, this is also a radius of 10, and this is 1.5 radians. And I could stick with radians if I want here, or I could just take those 1.5 radians and convert it to degrees, which might be a little easier to see. So 180 degrees is equal to pi radians. My radians will cancel, and that'll give me degrees. So I'm going to take 1.5 times 180 divided by pi, and that'll give me 86 degrees. So this is 86 degrees. And it doesn't matter if I work in radians or degrees, it's just easier to see. So I have an isosceles triangle. I know these base angles would be congruent. All three angles sum to 180. Or I could just know that area of a triangle, 1/2 one side, the other side, sine of the angle in between the two. I did that a little bit earlier. So I'm going to take in degree mode. This is important that the mode of my calculator corresponds to the units I'm using. So I'm in degree mode. I have sine of the answer there times 10 times 10 times 0.5, and the area of the triangle is 49.9. So the area of the sector is 75 minus the area of the triangle, right? Minus the area of the triangle. To give me area of that shaded region, which is 25.1 square units. So that would be how you do number 4 here. And then let's also take a look at number 6. This one's actually kind of interesting. So on number 6 here, a complete revolution, a full turn, is 360 degrees. So all the way around 360 degrees. If I split a degree, just like with an hour, into portions, they're called minutes, and there's 60 minutes equal 1 degree, or 60 seconds equal 1 minute. So there are 3,600 seconds in a degree, 60 minutes in a degree. Works just like our clock. So I have a central angle in my circle. That means at the center here. This central angle is only 1 minute. So it's only 1 minute wide. And then I know the radius of the Earth is 6,371 kilometers. So we're talking about an arc length. So I need to find the circumference. So the circumference of the whole circle is 2 pi r, or 2 pi 6,371 kilometers. And that's going to be all the way around the circle. So I have 6371 times 2 pi. That 40,000 is the circumference around the whole circle. And I don't want the whole circumference. I only want 1 minute of the total. So I'm going to multiply that by I only want 1 minute of the total. Well, how many minutes in a full revolution? It's going to be 360 degrees times 60 minutes. And that'll be the total number of minutes, right? So I want 1 of the total. So I can take that circumference. I'm going to divide it by 360 times 60. And it gives me 1.85. And that's going to be kilometers. So a nautical mile is 1.85 kilometers, or it's the equivalent of 1 minute of the circumference of the Earth, which is whatever 360 times 60 is. Okay, so that's section 12A and 12B in our IB math book for Math SL. Hopefully that helped. Thank you for watching. I appreciate hearing your comments below. If there's a better way to do these problems, please comment below. Thank you.